Welcome back to Calculus 1. This is a very exciting lecture. We are going to transition from talking about one part of calculus, what we have been so far in our course on differential calculus, and transition to learning about the other part of calculus called integral calculus. All right, now the title here is Approximating Area. We'll get to that shortly, but let's go back to when we started our course, a way that we kind of set up limits leading to defining the derivative. We tried to answer the tangent line problem. So coming out of pre-calculus where you learned a lot about graphs of functions, this is a very simple problem to state. Given a graph of a function and a point on that graph, here a comma f of a, find the equation of the tangent line. Now this was a kind of a good problem to start with because we can get an approximate answer by using the slope of a secant line. Now we're reviewing this because we're going to see this come back in how we start now integral calculus. So let's think back to the tangent line problem. We have a fixed point a comma f of a, and we looked at a point that's a little further away than that by h units. The x-coordinate would be a plus h, and you get that line there passing through those 2 points called a secant line. Now the secant line only requires algebra to answer it. Now the secant line, as you see here, doesn't kind of look very close to our tangent line sketched in red, but the secant line is a way we can start answering the question of finding the equation of the tangent line and getting an approximate answer. So I want you to think and keep in your mind what we did with the tangent line problem is going to come back through a lot of other calculus courses and other mathematics courses. We take a problem and we start trying to find an approximate answer. And then, as you see here and probably recall, because you remember all your earlier Calc 1 topics perfectly, we make our approximate answer better by taking a limit. For the tangent line problem, the limit was letting the second point approach the first. As that second point gets closer to the first one, the distance between the points, h, gets smaller. So we can make our secant line the approximate slope. We can make it exact by letting the distance between those 2 points, h, go to 0. So we introduce a limit, and that basically makes our approximate answer exact. We're going to see this come back in answering now a new problem for integral calculus, which is given the graph of a function, trying to find the area beneath it. Now, this does get a little bit complicated if the graph goes below the x-axis. We're not going to worry about that right now, since we're just introducing these concepts and kind of building the foundation. So we have a new problem. Given a graph, we're interested in finding the equation of the tangent line now, but between 2 points on the x-axis, labeled A and B, we're interested in finding the area beneath that graph between those x values. And you can see it shaded down there in red. Now the sides and bottom are straight. What makes this a little bit complicated is the curvy function on top. And this doesn't fit the formula for any kind of regular geometric shape, like a square or rectangle. Now we're going to see these ideas of using an approximate answer and exact answer come back in this lecture and the next lecture or two. Within our lecture today, we're going to be looking at not getting an exact answer, but just trying to approximate this area beneath the curve. In a following lecture, we'll then look at how we make that approximate answer better or exact. Okay, so this was kind of what we just mentioned. There's an outline that most calculus problems or theoretical concepts follow. Here, we're interested in finding the area beneath a curve. The first way we approach this is trying to get an approximate answer. So step one, we're going to look at conceptually a way to approximate that area beneath that graph. And then once we have that approximate answer, we then make the approximation better. Almost always in calculus, that involves some sort of limit. Before, it was a limit as h goes to 0. We'll see where the limit concept comes in here. All right, now this is actually an extremely old idea. This was developed rigorously by an ancient Greek philosopher / mathematician, Eudoxus, with what's called the method of exhaustion. And just in case you're not familiar with the notation there, BCE is before Common Era. And then CE, which we now live in, is the Common Era. So this is pretty old, over 2,000 years ago. Archimedes took the method of exhaustion and applied it to approximate pi. And Archimedes was regarded as one of the greatest mathematical minds in all of history. And what he did was rather remarkable, considering over 2,000 years ago, there wasn't calculus. There were the foundations of it with what's known as the method of exhaustion. And if we approach it as Archimedes did for finding an approximation for pi, let's think about area of a circle. Now we have a circle there, and what we ideally try to do is approximate a circle by a certain polygon. The more sides that we use, the more that polygon resembles a circle. As you increase the sides greatly, for instance, if I were to sketch a 20-sided polygon, it would look pretty much circular at this scale. So we put a polygon inside, or inscribe it inside the circle. The corners are tangent to the circle. And then we put a polygon just on the outside, also tangent to the circle. So we have an inner polygon that's a little too small compared to the area of a circle, and then an outer polygon where the area is a little too big. Here, with these three examples of a pentagon, hexagon, and octagon, 5, 6, and 8 sides, you can kind of see as you progress to the octagon, the number of sides starts to look more circular. Now, what Archimedes did, which is why he's one of the greatest mathematical minds in all of history, he used a 96gon. And I'm not even sure what the name for that is, and a Kakasa dodecamecadecahedron or something, but it has 96 sides. And he did that same idea. He put a 96-sided polygon inside the circle and had this underestimate for the area, 3 plus 10 over 71. And he put a 96-sided polygon on the outside and got an overestimate for the area of a circle, 3 plus 10 divided by 70. Now the area of the circle should be between them. As you use more sided polygons, the upper and lower bounds become very, very close. And this result is remarkably accurate. Take a look at the decimal representations for those two numbers, 3 plus 10 over 71 and 3 plus 10 over 70, and you'll find it's very close to pi. Before roughly the end of the 1800s, what we now call the number pi, it was known as Archimedes' constant in honor of this calculation. Now this is again the foundation of what we're going to be doing. We're going to take a certain area and approximate it by things that we know the area of. So let's say we have a graph. We have two values on the x-axis, a and b, and we're interested in finding the area beneath that. Now what we want to do is kind of approximate the area, like the method of exhaustion as we just kind of looked at, with figures or shapes that we know the area of. Now there's a lot of ways mathematically you can do this. What we're going to do in our Calc 1 course is we're going to approximate this area with a bunch of rectangles. And as it turns out, this will be kind of remarkably accurate, as we'll see within this lecture and what comes next. Now, what's nice about rectangles? Their area formula is rather simple. In this orientation, the rectangles are kind of oriented vertically. So we just need to know the width of the rectangle and the height, and we multiply. So the area of one rectangle would be the height times the width. All right, now we have to figure out a way to kind of approximate this area with a certain number of rectangles. So we're going to make it a little abstract right now. The concrete examples will follow shortly. And basically what we decide is how many rectangles we're going to approximate with. We're going to call that number of rectangles n. We take the interval that we're looking at, the area beneath the graph over, a to b, and we're going to basically divide that interval into n smaller intervals. So we'll split the big interval into n smaller or sub-intervals. They're going to be all equal width, so we take the total length of that interval, which is b minus a, and we divide it by the number of pieces we're splitting it into. So we would get the length of each subinterval, what we're going to call the width of a rectangle. We're going to note it as delta x, which is just the total length, b minus a of the interval, divided by the number of rectangles that we're using. So we have a way to calculate the width of a rectangle. We choose the number of rectangles that we're using, and we calculate the width. All right, the other dimension that we're going to need to get the area of a rectangle is not the width, but the height. Now, the way these rectangles are oriented, you can kind of see as you go over that interval from A to B, some of the rectangles are taller or narrower, a little shorter, and their heights are changing. Notice the heights change kind of corresponding to the shape of that graph. So what we're going to do is basically put rectangles that kind of touch, maybe being just below or hanging over the graph, right at that certain x value that we're picking. So at a certain x value, there's a height going from the x-axis to the graph. Just think, how do you figure out that distance from the x-axis to the graph? That is exactly the y or function value. So if we are looking at a rectangle at the x-coordinate x, that height going from the x-axis to the curve is exactly what f of x is. That's the y distance along the y-axis. So it's a remarkably simple idea. The widths are all going to be equal, what we're denoting as delta x, but the heights of each rectangle, as you see in our basic sketch, can change. We basically determine the height of each rectangle by a certain function value, f of x. And if we multiply that, f of x denotes the height, delta x denotes the width, we now have a way to find the area of one rectangle. That's kind of like the method of exhaustion. We have a kind of a polygon, but now we're looking at rectangles. All right, now you can see in our sketch, we're using several rectangles, 5 of them on that generic sketch, but that's just the area formula for one of them. Well, we just apply that formula to each of those 5 rectangles, for instance, in our sketch there, and then add or sum all those rectangular areas up. So pretty much what we have here is the way to calculate the area of one approximating element, an approximating rectangle, and then we just add up however many rectangles and rectangular areas we decided to use. All right, now just to kind of take a look at a few of those ideas, actually to have them written down, because sometimes ideas go very fast. Let's just point out that the interval we were looking at from A to B, that is divided or split into n subintervals of equal length or equal width. There's ways you can do this in higher level mathematics courses where the rectangles don't have the same width. We're not going to be looking at that. So in all of our questions on approximating area using rectangles, each rectangle will have the same width. We can calculate it, the total length of the interval, divided by the number of rectangles that we're using. All right, the next part is how we determine the heights of each rectangle. That again comes from the function value. We can determine the height at any point within each subinterval. Now let's take a look at the bigger interval, a to b, and let's just focus on one of those subintervals, one of those smaller intervals over which there would be a rectangle. Let's call that interval or subinterval c to d. Now there's some standard ways to do these approximations. For that subinterval, c to d, there's the left endpoint, which is c, and there's the right endpoint, d. The two standard ways to start by approximating area is just to be consistent, use the left endpoints for each subinterval, and at each of those left endpoints, we take that x value, plug it into the function f of x to determine the height of each rectangle. And the rectangle would go up and hit the graph and either be hanging underneath the graph or hanging over, depending on what the curve looks like. So if you use the left endpoints, we add up all those rectangular areas using the left endpoints to determine the heights. When we get this approximation, capital L with a subscript n, which denotes the sum of n rectangular areas using the left endpoints. Now you could alternatively, instead of using the left endpoints of each subinterval, use the right endpoints. And it's a similar calculation. You would determine the heights of each rectangle at all right endpoints for the subintervals, and then sum or add up all of those rectangular areas. So these are the two standard approximation methods: approximating rectangles by using left endpoints, or approximating rectangles by using right endpoints of each subinterval. We'll look at another way to do this using midpoints, but left and right endpoint approximations are standard. All right, let's go ahead and get to a simple concrete example so we can see how all this comes together. And it's a very simple graphical question. We're given the graph of y equals x squared, your basic parabola, and we're asked to consider the area beneath that graph over the interval from 0 to 4. Basically, what we're going to try to do here is find the area beneath the parabola from x value 0 to x value 4. The two parts ask us to approximate this using our two standard ways. We can approximate it in part A using the right endpoints of 4 rectangles. Notice the subscript 4 there tells you we're using 4 rectangles. And then in part B, we'll repeat this, but approximating the area using the left endpoints, still of 4 rectangles. All right, let's go ahead and start. We're going to try to visualize these calculations where possible. So let's start with a graph of y equals x squared. And we'll just draw a rough sketch by hand, looking at the interval of x values from 0 to 4. All right, if we split that interval from 0 to 4 into 4 pieces, the interval has total length 4. We divide by the number of rectangles that we're choosing, 4, or hold for this example. And what we get is each rectangle has width 1. The width, delta x, is 4 minus 0, the length of the interval, divided by 4. So we get the width of each rectangle is 1 unit. So we take our longer or total interval, 0 to 4, and divide it into 4 smaller intervals, each of length or width 1 unit. So this is pretty simple. We have the subintervals from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now, if we use here for part A, the right endpoints, we go to each subinterval. Let's start with 0 to 1. And we go to the right endpoint and then basically draw a rectangle up for the height that stops as soon as it hits the graph. And then we draw a rectangle over the interval, which if we're at the right endpoint, we determine the height at x equals 1, and then draw the rectangle to the left over that entire subinterval from 0 to 1. And what you can see here within that first rectangle that we sketched over the subinterval 0 to 1, the rectangle is a little too big. It's hanging over the graph. And you can probably see here that the 4 rectangles we're using are going to lead to an overestimate for this area. It's going to be a little too big. All right, so this is a visualization of the right endpoint using 4 rectangles. And basically, we determine the area of each of these 4 rectangles by taking our determined left or right endpoints here, and plugging those into the function x squared. It is the function values that represent the heights of each rectangle. And if you take a look at all 4 right endpoints, x equals 1, x equals 2, x equals 3, and x equals 4, we plug those into the function to get f of 1, f of 2, f of 3, and f of 4. Now, the function value is just representing the height. We have to multiply the height by the width, delta x, which we calculated that delta x as 1, the width of each rectangle. Now, this is a nice calculation since it worked out that the width, delta x, equals 1. So this calculation is really simple. The function f of x is x squared, square 1, 2, 3, and 4, multiply each of those by 1, and then add them up. Adding up there is adding up all 4 of those rectangular areas. And if you do that, should get this comes out to 30 units. Now from your sketch, you can see this is a little too big. Let's take a look at part B to see what we get. Now we're still using 4 rectangles, but instead of determining the heights of the rectangles at each right endpoint of the subintervals, we're going to determine the heights at the left endpoints of each subinterval. And if we take a look going all the way left to right, the first left endpoint is 0, then 1, then 2, the last left endpoint is 3. Now the first rectangle we sketched there on the subinterval 0 to 1, it's kind of degenerate. It's of 0 height. So I just drew a little red line on the x-axis there. All right, we go then to the next left endpoint, which is 1, and then we draw a line up representing the height. We hit the curve, and then we draw the rectangle over to the right from that, over the subinterval from 1 to 2. So you can see your rectangles here are beneath your graph. These 4 rectangular areas are going to be an underestimate. All right, now it's pretty much a similar calculation above, but our 4 left endpoints are a little bit different. They are 0, 1, 2, and 3. So we plug those left endpoints, 0, 1, 2, and 3, into the function. That determines the height. We multiply each of those heights by the width, delta x, which is still 1, and we get our underestimate as 14 units. All right, we're going to see more examples, but let's kind of take a look at some follow-ups to that. We saw from our sketches that the right endpoint approximation was a little too much, 30 units. The left endpoint approximation, which was 14 units, was a little too small. What we can conclude is that the exact area, whatever it is, we can't answer that yet. We're just interested in approximating an answer here for this lecture. our exact area should be somewhere between 14 and 30. Now, before our course ends, we'll have a very quick way to get the exact answer, the exact area, but we're not ready for that yet. All right, one way to improve your approximations, instead of using the left or right endpoints of each subinterval, you can use the midpoints of each subinterval. And that is another standard approximation method, which we'll just take a look at a quick example. So it's the same sketch, same graph. We're going to still use 4 rectangles. We take our total interval from 0 to 4, divide it into 4 pieces. So we have 4 rectangles, each of width 1 unit. Now take a look at your subintervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4. We're not using right now the right or left endpoints to determine our heights for the rectangles at. We're deciding right now to use the midpoints. Your 4 midpoints for each subinterval would be 0.5, 1.5, 2.5, and 3.5. Now, if we visualize what the midpoint approximation looks like with 4 rectangles, you'll actually see that this should be very accurate, since there is a little portion of the rectangle that hangs over, which is almost balanced in size by the amount that is 2 less left underneath the graph and between that rectangle. So it's kind of both at the same time a little too big and too small, which balances out, making this pretty much just right. And if you calculate the midpoint approximation here, the only thing that changes is the coordinate for each subinterval where you're determining the height, which are now 0.5, 1.5, 2.5, and 3.5. We still plug those into the function x squared. It's a little bit harder since we're squaring decimal values. But if you work that out, multiplying each height by the width, 1, you should get this comes out to 21 units, which is above, in our first comment, kind of what we expect. An accurate or exact answer should be somewhere between 14 and 30 from what we found in example 1. And 21 is right in the middle. Now, we don't have the tools yet for me to kind of explain where this exact area comes from. The exact area is precisely 64/3. Now, we will get to that before our course ends, but we're not ready for that yet. And if you approximate that as a decimal, it's about 21.33, which is really, really close to what we found with the midpoint approximation using 4 rectangles, 21 units. So using only 4 rectangles, but now the midpoints, we get an accurate approximation. All right, there is a third way, rather than using the midpoints to get an accurate approximation, which is the conceptual starting place for kind of the next lecture. Well, we can just get a better approximation by using more rectangles. Now, something happens to the rectangles, how we decided to use them. Remember, we are dividing our interval from A to B into n equal pieces, or n subintervals or rectangles. Now, what happens as we use more rectangles? What happens as n gets bigger? Notice in that fraction, n, the number of rectangles we're using, is in the denominator. As the denominator gets bigger, that whole fraction gets smaller. So as we increase the number of rectangles, the width, delta x, gets smaller. So let's see that in action here. Let's say, for example 1, instead of using 4 rectangles, we increase it, we double it, and use 8 rectangles. This will become really tedious to do by hand, but it's worth doing once. So we take our total interval of length 4, and now we're dividing it into 8 pieces. 4 divided by 8 is 1/2. That is our width, delta x. So we have 8 rectangles or subintervals, each of width or length 1/2 unit. Now, if you were to sketch this one is not too bad. Hopefully the visualization looks all right. But we have 8 rectangles. The right endpoint approximation is still an overestimate, but notice it kind of looks a little bit better of an approximation to what we had earlier just using 4. This one's a little bit tedious, but if you work it out, which definitely give yourself an attempt at, either pause the video or wait until the lecture ends, you should find that the right endpoint approximation comes out to 25.5. And just so you see your right endpoints, your first right endpoint would be 1/2, then 1, then 1.5, then 2, all the way up to your last right endpoint. Your last subinterval is from 3.5 to 4. 4 would be your last right endpoint. Still plug all those right endpoints into x squared and multiply by your new width, 1/2, and you should get this right endpoint approximation using 8 rectangles. Also go through and give yourself an attempt at repeating this, but for the left endpoint approximation, your first left endpoint would be 0. Your last left endpoint would be 3.5. You'll again get an under approximation, but it's a little bit narrower. Notice now our under approximation, 17.5, is a little bit closer to the exact answer, 21.33, that we looked at a few minutes ago. All right. Now, just so we kind of get an idea where this is going, beyond the scope of this lecture, but definitely within the next one, we'll find a way to make this approximate area or answer exact. And we basically take this improvement procedure using more rectangles to the extreme. Well, instead of using a large number of rectangles, let's just go all the way to the extreme. Let's use an infinite number of rectangles. And that's where the concept of a limit comes in. We take the limit as the number of rectangles that we're using goes to infinity. Now, this is conceptually a little bit bizarre from what we stated earlier, still on the screen. As you use more rectangles, the width, delta x, gets smaller. Notice in that expression, the formula for delta x, b minus a over n. As n goes to infinity, delta x goes to 0. So as we use more rectangles, they become narrower and narrower. In the limit, we're going to say they have infinitesimal width, which is basically the opposite concept of being infinitely big. Our rectangles will be infinitely narrower. But again, we'll save that for the next lecture. All right, let's just take a look at a related example, example 2, just a different function. And now we're asked to sketch and calculate the right endpoint approximation using 6 rectangles. So give yourself some time, pause the video, and we'll check in a few minutes. This one's a little more tedious since we're using not 4 rectangles, but 6. All right, welcome back. Let's go through this example. Hopefully, you're comfortable with the graph of e to the x. We're just going to be looking at the graph from 0 to 2. That's our interval in question. And with 6 rectangles, that's in the notation r sub x. So we're told to use 6 rectangles. We take our interval from 0 to 2. It has length 2 units. Divide that into 6 pieces. 2 divided by 6 is 1/3. So we have 6 rectangles, each of width or length 1/3 units. All right, and since we're told to use the right endpoints, going in order, your first right endpoint is a third. Your last right endpoint would be 2. So we have 6 rectangles. We plug in all 6 right endpoints of each subinterval into the function, which is here e to the x. And we multiply each of those function values by our calculated width, delta x, which is 1/3. So we have 6 terms representing the 6 rectangular areas. And if you work that out, just be careful and use parentheses if you're plugging these into your calculator. You should get all these exponentials multiplied by a third, adding up to about 7.51. And that would be our right endpoint approximation using 6 rectangles. All right, now those examples kind of set the foundation. The only thing changing is the function, but the basic procedure is the same. When we're asked to approximate area, we start by choosing how many rectangles that we're going to use. Usually you want to pick a small number, since if you do this by hand, you don't want to add up 100 rectangles, unless your professor's a real jerk. So we choose a small number of rectangles. We then use that number of rectangles, n, to calculate the width of each rectangle, the total length of the interval, b minus a, divided by the number of rectangles we chose to use. We then choose for each subinterval the endpoint where we're going to determine the height. Typically, it's the left endpoints or right endpoint of each of those n subintervals. And we basically plug in those endpoints, be it right or left endpoints, into the function that represents the height of each of those rectangles. Now, the function values by themselves, f of x, aren't enough to answer the question. F of x only represents the height. We have to multiply each height or function value at a certain right or left endpoint by the width, delta x. So we multiply height by width and then sum or add up all of those rectangular areas. And with certain examples, a small number of rectangles that we saw kind of gives a somewhat accurate approximation. Now that's basically it for this lecture. Again, the examples just change the function. Calculations are as tedious as we saw within example 1 and example 2. But where the next lecture goes is that brief comment we made about introducing limits. We get the exact area by taking the limit as the number of rectangle goes to infinity. So that will be content for our next lecture when we transition to giving the exact area. In this lecture, we're just focusing on approximating the area.